Hello there. We're going to start Unit 3, and this part of Unit 3 is going to be what I would just refer to as gas laws. Ideally, this is not your first time. Ideally, you have seen gas laws before in pre-AP chemistry or even on-level chemistry, and then this is review. But I don't like to start something like gases, a very important topic on the test, by assuming you remember anything. So I'm going to go off the assumption that you don't remember anything, and we're just going to try to build our understanding of gases as we go, and that's what we're up to today. So today we're going to we're going to look at pressure and temperature. Not all gas laws or anything like that. I'm only going to look today, again, not wanting to assume, on just pressure and temperature. Let's understand what pressure and temperature are, and then we'll have a solid foundation for building from for the rest of our look at gas laws. So a definition, this is worth writing down. Pressure is the force of particles colliding with the walls of a container. That's what pressure is. That's the definition they use on the AP exam. That would be something worth putting down to your notes, so pause if you need to. Now this part here in the middle where I say pressure is measured with a manometer if it's contained, or a barometer if it's just the atmospheric pressure, that is not likely anything that's going to be on the test. They'll use those words though, so I want you to just know what those words are referring to. So I'm going to go scuba diving, and before I go, of course, I check my tanks and I hold up the little indicator that tells me how much pressure is in the tanks. Because the scuba tanks are a contained gas, that little device is a manometer. Then I watch the weather reports and they tell me, oh, warm front's coming, cold front's coming, whatever. They tell us about the pressure of the atmosphere, and they will say the barometric pressure, as in they measured it with a barometer. Okay, so you don't need to know how those actually function, although it is cool. Just like go to Wikipedia real fast, look them up. It's rather interesting how it works. I love the story of Evangelista Torricelli, and I'm probably saying it very wrong, but I love the story of him building a barometer to make his measurements from that led to the idea of what pressure really is. Fortunately for him, he used mercury, and so his barometer only had to be about 1 meter long. Had he used water instead of mercury, it would have had to be something like 33 feet long. And obviously that would not have been at all practical even now compared to back then. So anyway, so barometer and manometer, words you'll see on the test possibly. You really don't need to know how they function. Just want to be sure you weren't confused by the vocabulary. Remember, I'm trying to tell you, don't panic. That would be like extra information that they would give you in a word problem. I cannot imagine, just my guess, but I cannot imagine it would be a question of what is the device used to measure the gas trapped in a container? And you have to pick manometer, barometer, or something else. Okay, I can't imagine a question like that. What you do also need to know, and I don't know if you need to write this down because it's on your formula chart for the AP exam. You should have one of those. If you don't own one of those, because you downloaded it, then you might want to go download it. But on the AP exam, they most certainly are going to use the identities, the equalities, whatever you want to use there, you need to know these. They're going to use that 1 atmosphere is equal to 760 millimeters of mercury. And that's probably like a 760.00000, as many zeros as you want. They don't get super hung up with sig digs on the AP exam, but you should always be practicing sig digs. That's what I'm expecting in class. Also the same as torr, okay, and they're torr for Torricelli, and millimeters of mercury because he literally had a tube, super long tube filled with mercury with a meter stick stuck up against it. And on days of high pressure, the mercury in the tube would go up, and he could measure a higher and higher and higher millimeter mercury amount because the zero is at the bottom. And then on days of low pressure, the mercury in the tube would be lower, and he could measure, down below. So that equality right there that I just boxed is on the AP formula chart. What's that mean? They're likely going to use the labels of atmospheres, millimeters of mercury, or torr in all their questions. So were you taught KPAs? Great. You probably won't need them on the test. Were you taught PSIs? Great. You probably won't need them on the test. All right. I'm going to say that atmospheres, millimeters of mercury, and torr are going to be the only necessary labels to understand on the test because that's all that's on the formula chart. Now, again, they could throw in other labels as extra information, but it would be just that, extra information, not things you need to solve the problem. Okay, let's try some pressure. You will need to be able to do this on the AP exam. You'll need to be able to convert from one unit of pressure of those three to a different one. So let's do some of that. Again, I'm going to do it with railroad tracks. That's what I call what I do. You could do it with fractions just as easily. I'll demonstrate both with the first one, and then I'm just going to do railroad tracks from there on out. But we're told the pressure in Chicago is 760 millimeters of mercury. That's my given. I'm looking for atmospheres. So I'm going to convert millimeters of mercury to atmospheres. I start with my given information. There's my 760 millimeters of mercury. And thanks to the formula chart, I know there are 760 millimeters of mercury in one atmosphere. Now, again, that equality right there came from the formula chart. That's how I know that. I don't memorize it. I just look it up. There we go. Millimeters of mercury cancels millimeters of mercury. The math I have to do is 766 divided by 760. This would be something they'd expect you to be able to do on the AP exam, okay? And they would expect you to be able to do it quickly. This, with these numbers, they'd expect you to do it with a calculator, okay? But you should already guess, this is just gonna be a little bit above 1 atmosphere, because 766 compared to 760 is not that much bigger. So when I round to the 3 significant digits I start with, I'm going to call it 101 atmospheres, and there's my answer. Now, how would you do that if you don't do railroad tracks and you do the fractions? Okay, so we go 760 millimeters of mercury times the fraction of 1 atmosphere is the same as 760 millimeters of mercury. Oh, look, it's the exact same thing. So don't get hung up on the form, how they do it on the test. It's kind of interesting. All the time, the test graders that I know, like we all kind of do it this way with the railroad track. But then on the official, here's how you get the answer document that comes from the AP test writers, they will only show it with the fractions. I think they're just trying to, you know, make it look harder than it is or something like that. I don't know. Or they just don't know how to draw railroad tracks in a document. Maybe that's it. But there you go. No difference in formatting, no difference in the math. Do it whichever way you are comfortable with. All right, let's try the next one. Pressure in Los Angeles, 762.7 torr. So 762.7 torr. I also already see I have 4 sig digs, so round to 4 sig digs in my answer. I'm looking for ATMs. Okay, so again, 760 torr is the same as 1 ATM, and those are like unlimited significant digit numbers. They're definitions. They have been declared to be equal. So I'm going to take now 762.7 and divide it by 760. And when I round to 4 significant digits, I get 1.004 ATMs. So there we go. That's how we do that. They will absolutely expect that you are able to convert your pressure units on the AP exam. So be able to do that. Why do you need to be able to do that? Because our formulas, when you're plugging it in, the pressure will have to either match, all the pressures in the problem must match, or if you're using an R for the ideal gas law of the typical liter atmosphere mole K, you will need to have it in atmospheres, and they're likely going to give it to you in millimeters of mercury or torr then to force you to do that conversion, so they know you can do the conversion. So be able to do these conversions is what I'm trying to tell you. 2 more examples, and then we'll move on from this topic of doing, oh, I needed to clear that. This topic of being able to do pressure conversions. Okay. Pressure in New York. I should have picked some numbers that's less than 1. That would have been a little more interesting. Sorry. Pressure in New York's 101 atmospheres. How many millimeters of mercury is this? So 1.01 atmospheres. This time I know atmospheres is on the bottom to match diagonal. 1 atmosphere has been declared to be 760 millimeters of mercury. And I'm going to round to 3 significant digits because that's what I'm starting with. So 1.01 times 760, I get 768 millimeters of mercury. There's my answer, boom, done. So this would not likely be anything that's worth points. This is something that you're doing in order to use an equation that would be worth points. But every once in a while, there are points just for doing a proper conversion of something. So I do recommend showing this if you do this on the test. You can do it off to the margin. You could do it just right there where you're working. It won't matter. We look at everything. I would recommend just putting it right there where you're working. I mean, this is part of your work, but you need to be able to do these. Okay, so pressure in Death Valley, 1.03 atmospheres. I would expect the pressure to be more in Death Valley than at sea level because Death Valley is below sea level. The higher up you are, the less the pressure is, mostly because there's less gas particles above you pushing down on you. So if you're below sea level, the greater the pressure ought to be because in theory, there's more gas particles above you pushing down on you. So there you go. So 1 atmosphere is now going to be on the bottom, so I can cancel out those units, has been declared to be 760 torr. And there I go. 1.03 times 760. I'm going to round to 3 significant digits, 783 torr. And there's my work. So there we go. Yeah, I hope you found that to be super easy. But again, I didn't want to assume you had ever practiced doing those conversions. And so I wanted to be sure that we did them together. And there you go. Okay, let's talk about temperature. Because as I said, we're going to look at pressure and temperature. And I can't get why. There we go. Finally got the right button. Okay. So let's talk about temperature. Here is a definition of temperature. You want to write this into your notes. It is the average kinetic energy of the particles in matter. Now, they actually put the kinetic energy formula on the AP exam. It is actually there. I'm going to grab a pen here. Okay. This formula, like you see it, is on the AP exam. It is. It's there. Why would they want you? They would not want you to calculate kinetic energy. It's there to remind you how it is calculated. To have more kinetic energy, I could either have more mass, which not likely that's going to happen. I mean, the particle's mass is its mass, and then you can't change that. But it's also the velocity squared, so there's most definitely that. What does this mean for us for the most part? This means the greater the temperature, the greater the average kinetic energy of the particles are. Now I'm going to stress the average part, you'll see why in a little bit. Okay, but it's not saying that all of them, if I warm something up, are going to have more kinetic energy. It's just I get the average of the particles to have more energy. On average, they have more energy if I heat them up. On average, they'll have less kinetic energy if I've watched the temperature goes down. So temperature is a measure of the average kinetic energy of the particles in a sample. And I can take the temperature of a solid. It's not super thrilling, but I can do that. It's temperatures of gases we look at closely because those can change so easily. But let's move on. On the AP test, this is on the formula chart. Kelvins equals degrees Celsius plus 273.15. I don't know if you've ever seen this equation. It is, again, on your formula chart. Here's the thing. For gas laws, okay, for gas laws, all the math that you do with gas laws, the temperature must be in kelvins. Must be in kelvins. But they're not likely to measure that in the laboratory. And so they're not likely to give you that data on the test. They're likely to give it to you in Celsius, just like we would in our lab in our classroom. We put in a Celsius thermometer. It's up to you to convert to kelvins by adding 273.15. And then, of course, round to your significant digits. Okay? So be fully aware of this situation, right? And I want to point this out while we're talking about temperatures and converting to kelvins. We do have a standard temperature for gas laws. And the standard temperature, I'm going to just call it ST. That's supposed to be an S, sorry. ST, standard temperature. Well, that didn't work. I'm sorry, I just lost my pen, and I don't know why. Okay, so standard temperature. Seriously, I want my ink pen. Give me my ink pen. I give up. I have a hate-hate relationship with technology. I'm not thrilled with what's going on right now. Let's get back to where we were. Okay, my apologies. I think I need to adjust a setting real fast here. So sorry to take up your time with this. My mouse, for some reason, is just not liking me today. Okay. All right. Gonna try to breathe a sigh of relief. Hopefully things are better. Sorry about that. Okay. So as I was saying, there's a standard temperature for gas laws work. Okay, let me get back to where I can draw. I want drawing, and I want yellow. Can you give me that? Yay! Okay. Standard temperature for gas laws is 0 degrees Celsius. Every other field of chemistry, standard temperature is 25 degrees Celsius room temperature, even though I would not want to be in that room. That's a hot room. Okay. 0 degrees Celsius for gas laws. Why? Because this was invented long before the internet was, and no one talked to each other over email to decide ahead of time what temperature to do things at. So the people that were doing gas laws and the people that were doing everything else never talked, and they picked different temperatures. That's what happened. So understand, standard temperature 0 degrees Celsius. So when I add 273.15 to it, that means standard temperature is 273.15 kelvins. Okay, standard temperature. Those are our standards. Not saying that's the number that always goes in your equations. I would never, that's not at all what I'm saying. I'm just saying when it says on the test standard temperature, it's telling you those numbers. Okay, next up. Nope, I need to close this real fast. There we go. Next up, there we go. Okay, so for a couple summers while I was in college, I really wanted to get far, far away from where I had been living and decided to go to New Hampshire. And while I worked for this summer camp at New Hampshire, they had their one of their big deals. Once every week, they took a trip of hikers up to the top of Mount Monadnock. They were all like, "Oh, you got to see Mount Monadnock." Blah, blah, blah. Okay, so I did it once, and I trekked up there, and you know the view's pretty good because of the glacial action during the Ice Age. Like everything is flat except for this one particular mount. So I'm told I could see 4 different states from there. Now, also, those states are itty-bitty tiny up in the New England area, if you didn't notice, okay? So I'm not really surprised. Drove through Rhode Island in less than 2 hours. That boggled my mind. Like, I'm used to driving for 2 hours and not being anywhere close to leaving a state. So, but anyway, they're oh so proud of their mountain right there that you could climb for a day. You know, we'd even climb up there in the morning and have some time to take a little snack and then walk back and even get back in time for a late lunch. And, you know, okay, I'm glad they enjoyed it. I've also been to the Appalachians and to the Rocky Mountains, and I'm sorry, Mount Monadnock doesn't count for anything, sorry. Anyway, while I was there one summer, they hit a record for the most or largest temperature change that occurred on the top of that mountain, because there's a weather station at the top, in one day. It started at 1 degree Celsius in the morning, and it went to 30 degrees Celsius that afternoon after the sun had been baking it for a while. And I got to thinking, I mean, really, it's not that steep a thing. What if someone like drove a Jeep up to the top and like left it parked there? So in the morning, you drive it up, and your tire pressures are like 30 psi's. What would the pressure in the tires be then by the afternoon? I mean, really important question, because I don't want my tires to go boom, right? Okay, so here's how not to do it. Now, first off, the equation I'm going to do, I'm going to be relating pressure and temperature. If you did gas law as well in pre-AP, you will remember P1 over T1 equals P2 over T2. If you don't have a clue what I'm talking about here, it's okay. You don't have to know. I will later in a different video go over how to get that equation. It's not hard at all. That's my equation. So my first pressure, my pressure in the morning was 31 psi's, and in the morning it was 30 degrees Celsius. No, 1 degree Celsius. I had too many 30s going on it. And then the afternoon, I don't know what my tire pressure was. It got to be 30 degrees Celsius that afternoon. So I'm going to solve for X. So I, you know, cross multiply, divide, bat and ball, whatever you, butterfly. I don't even know what they call it in math class. They say, what happened to calling it cross multiply, divide? I don't get it. But I'm going to cross multiply, divide, and I see my answer for the afternoon tire pressure is 900 psi's. So I'm a little worried because my car, I'm supposed to fill it to 32 psi's, it says. And it says right there on the tire, don't fill it above 58 psi's. Like if I had my car up there and my tire pressure suddenly was 900 psi's, like my tires are inflating like balloons and popping. That would be awful. I'd never make it down. Well, that is not what's going to happen. That's why I did this in these area over here where it says incorrect. You don't do it that way. What mistake did I make? I did not convert to kelvins. You must use temperature in kelvins for gases. Must. It actually would work fine for almost any other applications to have it in kelvins too, but in gases specifically, you must have it in kelvins. So be sure you have it in kelvins. Okay, let's do it again, but this time let's do it correctly. So again, 30 psi's and 1 degree Celsius added to 273.15 and then rounding to sig digs because I only have that 1. 2, okay, well let's round off to the ones place. Let's just say that. It is not a very accurate temperature measurement. I should have actually looked up the very accurate measurements, but 274 kelvins. And then I want to know what the new pressure is, and then 30 added to 273 is 303 kelvins. Okay, so there we go. I'm going to grab my calculator because this I can't do in my head. Still going to cross multiply, divide. And I find my tire pressure in the afternoon in the super hot, drastic change of the heat of the day at the top of Mount Monadnock where the air is thin. Yeah, they were telling me that. I'm like, no, this is not a difference, no. Anyway, my tire pressure is 33 PSIs. That's reality. That's what would truly happen if I had a Jeep up on the top of Mount Monadnock with 30 PSIs in the morning at 1 degrees. The tires are gonna be just fine. Why is it so drastic a difference? Because of where the zero mark is. Remember, kelvins have the zero mark at absolute zero. Celsius, Mr. Celsius, like put his zero mark not even close to absolute zero. He put it where water freezes. And water, we know, can get much, much colder than zero. So you need the Kelvin scale. You need to have no negative numbers in your temperatures. Because if I had a negative number there, that means I would get a negative pressure. What in the world's in it? There's no such thing as negative pressure. The lowest pressure I could get is zero, and the lowest Kelvin I can get is zero. Celsius will not work for gas loss. Don't use it for gas loss. Always use kelvins, please. They put that equation on the formula chart to remind you to use kelvins. Please, please, please use kelvins. Thank you. Okay. Let's talk about temperature. You're like, already, weren't we already talking about temperature? I know. We're going to talk about graphing temperature. What did we say temperature was? A measure of the average kinetic. And how in the world do we know it's an average? Because we analyze it and we make cool lifting graphs like this one. Look at what we got here. I'm going to switch to a color that's going to show up. I'm going to go with kind of a bluish purple here. Okay. Now remember, temperature is a measure of average kinetic energy, and kinetic energy, I guess it's just a blue, is 1/2 mv squared. So here we have number of molecules or particles of the gas. Here I have the speed, aka the velocity. We just don't need to care about the direction. They have a direction, absolutely, we just don't need to care about them. So speed, velocity, same. This is showing me all the different speeds and therefore all the different kinetic energies. Do you see all the different velocities? Tell me all the different possible kinetic energies the gas particles have. But what do I see? The vast majority of them have that much speed. The average speed is there. Therefore, the average kinetic energy is whatever that number would be times mass, well, squared times mass times half, okay? So that's what it's showing. This is called a Maxwell-Boltzmann distribution. They love these graphs on the AP test. I would be shocked if you got through an AP test that didn't have one of these graphs. In fact, I had the, let's call it joy of last summer grading a question that had this graph, and students had to tell me about it. Very few students got it correct. I don't know why. It's easy points. Most of them that were close but didn't get the points missed the keyword average. This does not show just the kinetic energy. This shows all the kinetic energy so that I can easily pick out the average kinetic energy. Okay. So this is not really a big deal in and of itself. Let's look at this, though. They could totally ask you, how would this look different if the matter was cooled? So let's talk about what I expect. For cooling, we mean temperature goes down. If temperature goes down, the only way the temperature could have gone down is if the average kinetic energy went down. How would I show on this graph that the average kinetic energy, not all the kinetic energies, but the average kinetic energy went down? Maybe a curve, my drawing skills are awful, I know, but maybe a curve like this. Now notice I'm kind of sort of starting in the same place and I'm ending in the same place because not all the particles will at all have a decrease in speed. But the average now, okay, my new average speed is like there. And my old average, I'm going to switch to a red so I can kind of make this look, you know, distinct. My old average was, oh, look, at a lower temperature, the average speed is lower. Therefore, I know the average kinetic energy would calculate out to be lower. That's the sort of thing they would want to know on the test. It would not surprise me if they ask you to draw just like I just drew. Give you a graph with one line and ask you to draw the second. Or I've seen ones where they give you the graph with both lines or maybe more and ask you to label. They're like, data was taken when it was at 100 Kelvin, data was taken when it's at 200 Kelvin, label the temperatures on the graph. You would want to say that the lower temperature was the lower one, the one with the least average speed, and you'd want to say the higher temperature was the one with the greater average speed. Easy points, but you have to have a clue what this graph is. Sadly, most students, I would say, have not ever seen a graph like this in AP, and that's a sad thing. Because again, it's just graph reading, it's easy points. Keyword though, when you're looking at a graph like this. I mean, like, I'm usually not a stickler for vocabulary when you're answering questions on the test, but trust me on this. If you're looking at the Maxwell-Boltzmann distribution, the word average is super important. Okay. Let's try something else. How would it change if it was warmed? I'm going to pick a dark green this time. So I'm going to warm it up. Well, can you guess how it would look? Now, notice, again, I'm going to kind of start where I was because there's going to be some particles still with almost no energy, even though I'm warming it up. But it's going to kind of like do something like this. And I may or may not end in a similar place. There's still going to be particles. Now, good thing it's not an art test because that drawing was pretty bad. But there's going to be some particles, regardless of the temperature, that always have an extreme amount of velocity. And then there's going to be some, regardless of the temperature, that always have almost no velocity. It's just the way life goes. What's this show us? The average speed is now greater. Therefore, the average kinetic energy is going to be greater. So if the temperature increases, I know that means the average kinetic energy increased. I must assume that meant the average speed has increased. Do you see how those three connect? Because those three connect. And that is a good scientific connection between temperature, kinetic energy, and velocity. So speed, velocity. So be sure that you know that connection correctly and you can discuss it in words correctly. Let's try something else. I grabbed this one. I liked it. I searched Google for Maxwell-Boltzmann distributions. One of the many images that came up was this. I like it a lot. Notice things that I've been trying to say all along. Like, it's almost as if I knew what I was talking about. Shh, don't let my secret out, okay? I'm gonna grab purple this time because there's no purple line on here. No, regardless of the temperature, there are going to be a few particles that almost have no energy at all. Notice how they all kind of end in the same location. Regardless of the temperature, there's going to be a few particles that always have an extreme high amount of speed or velocity, meaning a constantly high amount of kinetic energy. And then notice how as the temperature changes, typical things we see. As you increase temperature, the curves tend to flatten and they absolutely spread out. And so now I could drop some lines. I'm going to try and color code this. So my average green looks to be around a 1, whatever that 1's representing, okay? My average for yellow, I don't think I drew that straight, looks like a 0.9. Okay, my average for orange, I don't know if this is worth the time to draw each time, looks to be like a 0.8. You get the idea, right? As the temperature increases, the average kinetic energy of the molecules increase because we see the average velocity of the molecules are increasing. And we can say that in reverse. As the temperature decreases, notice the peaks get narrower. We really do actually get, now there's still always a few that have an extreme amount on both ends, but we tend to get a tighter range on the spread, okay, of the velocities there. But as we decrease temperature, the average kinetic energy must be decreasing because we see there's a decreasing in the average velocity or speed of the particles. So, easy points on the test. I hope you'd agree. I wouldn't be surprised if they asked you to draw. I can't imagine they'd ask you to draw 5 of them like I have here. Maybe up to 3, like they do one in the middle and ask you to draw one warm or one cold, or maybe just one. Maybe no drawing at all and just label it or analyze it. You ought to be able to handle all of those. All right, so we have discussed pressure. We've discussed its definition, what it is. We've discussed how to change units from one thing to another. We have now thoroughly discussed what temperature is, and we did a couple conversions. I think you'll find it easy. Just a reminder, if your Celsius is negative, you still add 273.15 to it. It just will be a number less than 273.15 when you're done. We can handle that. Also a reminder, if you're given kelvins and for some weird reason you want Celsius, I don't recall a time the AP exam ever asked you go from Kelvin to Celsius. They normally just ask you to go from Celsius to Kelvin. But if that is the case, then instead of adding 273.15, you subtract. The formula is there on your formula chart. Just rearrange it, solve for Celsius, and there's your answer. Okay, so just wanted to point that out. But this, you're staring at a graphical representation of what temperature is. This is the definition of temperature right before your eyes in graphic form. Very important chart because of that. But also know what temperature is in words. It is a measure of the average kinetic energy of the particles in the sample. All right, so hopefully that has been a great, like I said, I wanted to intro temperature and pressure. I did not want to take for granted it's a review. If it was a review, all the better. Okay, so that's it for us. I wish you luck on your practice. Be sure you get into Canvas and practice, 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 and I will see you later.